In 1875, the heaviest locomotive in Britain weighed 45 tons. Engineers at the Midland Railway designed a viaduct to carry 180 tons per axle. Trains that would not exist for another 50 years. The stone piers they built, each one 6 feet thick, at the base, were condemned as extravagant waste by company accountants who saw only immediate costs. Today, 49 years later, those same piers carry freight trains weighing 400 tons. The accountants are forgotten. The viaduct endures. The Settle Carlisle Railway was an act of corporate defiance. In 1866, the Midland Railway demanded access to Scotland. The London and North Western Railway, which controlled the existing routes, refused. Parliament granted the Midland permission to build their own line, 72 miles through the Pennines, crossing terrain no mainline railway had ever attempted. The route would require 21 viaducts and 14 tunnels. Critics called it impossible. The Midland called it necessary. The Ribblehead Viaduct would be the most challenging. The line had to cross Batty Moss, a peat bog 200 feet deep in places, sitting atop limestone bedrock, riddled with underground streams. The nearest town was 6 miles away. There was no local labor force, no existing infrastructure, no shelter from Pennine weather that could drop temperatures below freezing 9 months of the year. The site was exposed, remote, and unforgiving. The Midland's chief engineer, John Crossley, surveyed the location in 1869 and calculated what would be required. 24 arches, 104 feet high at the deepest point, quarter-mile length. Foundations sunk through unstable ground to bedrock 30 feet below the surface. Most engineers would have designed for the loads of 1869 40-ton locomotives pulling 20-ton wagons. Calculate the stress, add a modest safety margin, minimize materials, complete the work within budget. Crossley refused. He had watched railway technology evolve over 20 years. Locomotives were growing heavier, trains longer, speeds faster. The structure he designed in 1869 might serve trains in 1900, 1920. The structure had to be right the first time, not for the present, but for an unknowable future. The specification he wrote called for limestone piers 6 feet thick at the base, tapering to 5 feet at the arch spring point. Contemporary viaducts of similar height used piers 4 feet thick. Crossley added 2 feet. Not because his calculations showed structural need. The mathematics demonstrated that 4 feet would suffice for expected loads, but because he refused to trust the future to remain static. Train weights might double. Track maintenance might decline. Extreme weather might exceed recorded precedents. These were uncertainty mathematics could not eliminate. Extra thickness was insurance against the unknown. Construction began in 1870. The first challenge was reaching bedrock. Batty Moss consisted of peat, clay, and glacial till laid down 10,000 years ago, when ice sheets retreated from the Pennines. This was not stable ground. Foundations had to penetrate to limestone. Contractors sank test shafts at each pier location, probing for solid rock. Some reached bedrock at 15 feet. Others required 30. One shaft encountered an underground stream and flooded before hitting rock at 35 feet. The variation meant each pier would require individual foundation design, calculated separately, built specifically for local conditions. The workforce assembled slowly. The Midland contracted with John Sharland, an experienced railway builder who had worked on difficult projects in Wales and Scotland. Sharland brought experienced gangers and masons from previous jobs. Local men from Settle and Hawes joined when they could, but farming took precedence during spring and summer. The Midland built a temporary village at Batty Green, wooden barracks, a hospital, a school, even a post office. By 1871, more than 2,000 workers lived in the camps, scattered along the Settle Carlisle route. Ribblehead had the largest concentration, 600 men at peak construction. This was Carboniferous limestone, 300 million years old, dense and durable. Each block was cut by hand, shaped by masons using traditional methods unchanged since medieval times. The blocks varied in size depending on their position in the structure. Foundation courses used stones weighing 2 tons. Arch voussoirs were smaller, shaped to precise angles, fitted together without metal reinforcement. The mortar specification called for hydraulic lime mixed with crushed stone aggregate, capable of setting in damp conditions, resistant to freeze-thaw cycles, stronger over time as chemical curing continued. Each pier required a cofferdam, timber sheet piling driven into the bog, pumped dry, excavated to bedrock. The cofferdams leaked constantly. Workers labored in mud and standing water, shoveling by hand, hauling spoil in wheelbarrows up wooden ramps. Winter made the work brutal. Temperatures regularly dropped below freezing. Peat froze solid. Tools broke. Men suffered frostbite. The hospital at Batty Green treated pneumonia, tuberculosis, and injuries from falling tools and collapsing excavations. Deaths were common. Exact records were not kept. Victorian construction sites did not maintain comprehensive safety statistics, but contemporary accounts mention dozens of burials in nearby Chapel Lane. Once bedrock was reached, mass concrete was laid, Thames ballast, sand and Portland cement, mixed on site in wooden troughs, wheelbarrowed into the excavation, tamped, solid with wooden beaters. The concrete was laid in courses, each one allowed to cure before the next was added. Foundation pours took weeks. There was no rushing the chemistry. Portland cement needed time and moisture to achieve full strength. The contractors waited. Above the concrete, limestone masonry began. Each course was laid in hydraulic lime mortar. The blocks were positioned using wooden templates that established the pier taper and alignment. Masons checked their work with plumb lines and spirit levels. Inspectors examined every joint. Poorly fitted stones were rejected and recut. There were no exceptions. The piers rose slowly. Yards per month, not feet per week. By the end of 1872, the tallest piers had reached 40 feet. The arches had not yet begun. The arches presented a different challenge. Each span was 45 feet wide. Not extraordinary by Victorian standards, but the height created complications. Centering the wooden framework that supports an arch during construction had to be built from ground level, rising 100 feet in some locations. This required timber scaffolding, complex bracing, and precise carpentry. The centering had to hold the weight of the entire arch until the keystone was placed and the mortar cured. If the centering shifted or collapsed before completion, the entire arch would fail. The arch stones were cut to precise angles. Each voussoir had to fit its neighbors exactly, transferring load through compression to the piers below. There was no mortar strength holding the arch together, only gravity and geometry. Once the keystone was placed, the arch became self-supporting. The centering could be removed, lowered, and repositioned for the next span. The process repeated 24 times across the viaduct's length. Weather remained a constant adversary. The Pennines experienced some of England's harshest conditions. Rain fell 200 days per year. Snow arrived as early as October, lasted until April. Wind speeds exceeded 50 miles per hour during winter storms. Work stopped frequently. Mortar would not cure below freezing. Stone could not be laid safely in high winds. The schedule stretched. Costs overran. The Midland Railways Board questioned the expense repeatedly. Crossley defended every specification. The alternative was not savings. It was eventual failure and catastrophic replacement costs. By 1874, 18 of the 24 arches were complete. The viaduct had taken shape, a quarter-mile of stone spanning Batty Moss, high enough that trains crossing it would disappear into low cloud. The structure dominated the landscape. Farmers in the valley below watched its progress with a mixture of awe and skepticism. Nothing that large, that exposed, that ambitious had ever been built in the Pennines. Surely it would not survive the first hard winter. Surely the foundations would sink into the bottom. Surely the cost would bankrupt the railway. None of those predictions proved accurate. The final arch was completed in February 18. Track was laid in April. Ballast was spread. The line was inspected and approved. The first train crossed Ribblehead Viaduct on May 1, 1876. A Midland Railway express hauled by a 40-ton locomotive, traveling at 40 miles per hour. The viaduct did not flex. The arches did not crack. The piers stood firm. Critics fell silent. The structure carried traffic for 50 years without significant maintenance. Trains grew heavier. The 40-ton locomotives of 1876 gave way to 60-ton designs in 1900, 80-ton in the viaduct carried them all comfortably. The 6-foot piers, condemned as wasteful in 1870, proved pressure. Modern stress analysis, conducted in the 1980s using computational methods unavailable to Victorian engineers, confirmed that Crossley's design included safety factors exceeding 5 to 1 for the trains of his era, meaning the structure could handle 5 times the expected load. This was not accidental. This was deliberate over-engineering. The viaduct survived challenges Crossley could not have anticipated. World War II brought heavy freight traffic, military supplies, coal, steel, ammunition. Trains ran continuously, often exceeding peacetime load limits. The structure absorbed the stress without complaint. Post-war modernization brought diesel locomotives weighing 120 tons, freight wagons carrying 30-ton loads, passenger trains running at 70 miles per hour. The viaduct, designed for steam engines in 1869, handled diesel and electric traction without modification. Maintenance costs for the viaducts and tunnels seemed prohibitive. Ribblehead was inspected in detail. Engineers expected to find a deteriorating structure requiring expensive repairs or replacement. They found limestone in near-perfect condition. The mortar joints remained sound. The foundations showed no settlement. The piers exhibited no cracks, no spalling, no structural distress. The viaduct built in 1875 was sounder than concrete bridges built in 1960. Preservationists, local communities and railway enthusiasts campaigned to keep the route open. In 1989, the government abandoned closure plans. The Settle-Carlisle line was designated a protected heritage route. Investment followed. Track was renewed. Stations were restored. Tourism increased. Today, the line carries passenger trains daily and occasional freight. The trains are heavier than ever. Modern passenger units weigh 150 tons, freight wagons up to 40 tons each. The viaduct, designed for 45-ton locomotives pulling 20-ton wagons, now carries trains 400 tons in total weight. This is 9 times the load anticipated in 18. The safety margin Crossley built into the design remains unexhausted. Modern structural analysis confirms the viaduct could handle significantly heavier loads, potentially double the current traffic. The 6-foot piers have capacity to spare. The limestone arches show no signs of stress. The foundations, sunk through 30 feet of peat to solid bedrock, remain stable. Engineers today study the structure not as historical curiosity but as practical reference. The design principles, conservative load assumptions, generous safety factors, durable materials, thorough foundations represent an approach modern infrastructure rarely follows. Contemporary railway bridges are designed to minimum safety standards. Materials are optimized for cost. Replacement is anticipated within 60 to 75 years. This approach minimizes initial investment and allows for technological improvement with each generation. It also means constant reconstruction, perpetual disruption and accumulated expense. The Settle-Carlisle viaducts were expensive to build. The Ribblehead structure alone cost £42,000 in 1875 currency, equivalent to roughly £6 million today. But spread across 49 years of service, the cost becomes negligible. Modern bridges replaced twice per century incur capital costs repeatedly, plus maintenance, plus traffic disruption. The Victorian approach, expensive initially, becomes economical over time. The irony is that modern materials should enable even greater permanence than Victorian limestone and lime mortar. High-strength concrete, steel reinforcement, corrosion-resistant alloys. These materials outperform anything available in the 1860s, yet modern structures rarely last as long. The difference lies not in materials, but in intent. Victorian engineers designed for permanence because they could not predict the future and had no opportunity for replacement. Modern engineers design for replacement because project finance assumes it. The materials are better. The philosophy is shorter term. The Crossley died in 1879. 4 years after Ribblehead opened. He did not live to see the viaduct carry 100-ton locomotives, survive 2 world wars or outlast dozens of supposedly superior structures built with 20th century technology, but he built it knowing it would. The 6-foot piers, the 30-foot foundations, the hydraulic lime mortar. These were not accidents or miscalculation, they were deliberate choices, made by an engineer who understood that infrastructure serves not one generation but many, and that permanence, though expensive initially, costs less than anything temporary. The Riverbed Viaduct stands today, carrying trains 400 tons in weight across Batty Moss. The limestone blocks remain sound. The mortar joints show no deterioration. The foundations have not settled. It is not a museum piece or preserved relic. It is active infrastructure, doing the job it was built for, carrying loads 9 times heavier than existed when construction began. Victorian engineers are sometimes accused of overbuilding, of wasting resources on excessive strength, unnecessary thickness, extravagant foundation. Riverbed suggests a different interpretation. They were not overbuilding, they were building correctly. They simply refused to assume the future would be gentle, and history proved them right.